Hi everyone, so I'm going to introduce to you about game theory. In game theory, there are at least one player. For example, this is player 1, this is player 2, and this is the respective strategy. Say if these two person, right, is discussing whether they are going to watch a snooker or film. So assume this is the happiness level. So say if we plot this to a matrix table, right, so this is called as a pair of matrix. Then we are going to identify a few things. So the first thing we are going to look at dominant strategy. Dominant strategy is the strategy that gives the player highest payoff, okay? It gives the player highest payoff irrespective of the strategy selected by other players, okay? So meaning if Brian wants to have a dominant strategy, then his payoff must be highest, okay? So if we find both players in a true game have a dominant strategy. If both these players have a dominant strategy, right, then there is a dominant strategy equilibrium. I call this as DSE, okay? Dominant strategy equilibrium. Even if the equilibrium is not a Pareto efficient, if it's not a Pareto efficient, they maybe still have a dominant strategy equilibrium, okay? Later we are going to look at the example, what do we mean? So right now you only keep in your head, it may not be Pareto efficient, and when every player play his dominant strategy in the game, it's called as DSE, okay? Dominant strategy equilibrium. So let's look at this table. The first, right, so if you want to determine if there's a dominant strategy, so let's say Brian. If Brian watch snooker, right? If Brian watch snooker, what can Anna watch? Anna can either watch snooker too, or Anna can choose to watch film, okay? In this case, Anna is worse off, okay? Anna is worse off. Her happiness level is 5, okay? So this is not called as dominant strategy. This is also not known as dominant strategy. So Anna don't have a dominant strategy for now, okay? So Anna don't have a dominant strategy, okay? So what if Brian choose to watch film? So if Brian choose to watch film, right, what can Anna do? Anna can choose to watch snooker and the payoff is 1, okay? And then the payoff for this one equivalent, right? If it's equivalent, we don't call this as dominant strategy also. So Anna totally don't have dominant strategy, okay? Anna don't have dominant strategy. So how about Brian? If Anna choose to watch snooker, Brian can either choose to watch snooker or film, right? So if Brian choose to watch snooker, right? So 8 is higher than 5, right? So this is the Brian's dominant strategy, okay? Brian dominant strategy. 2 and 1, is it higher? If Brian choose to watch film also, right? This is also considered as dominant strategy, okay? Dominant strategy. About 6 and 2. 6, if Brian choose to watch snooker, if Anna choose to watch film, and Brian choose to watch snooker also, it's also known as a dominant strategy, okay? So how about 4 vs 4? If 4 vs 4 is the same, right, then this is not dominant strategy, okay? This is not dominant strategy. So in this scenario, right, there's no dominant strategy for Anna at all. Mostly is Brian. Brian have a few choice, okay? So let's look at how about the dominant strategy equilibrium. To be a dominant strategy equilibrium, right, each of the player have to choose their own dominant strategy. So in this case, right, Anna don't have any dominant strategy. So the answer is there's no dominant strategy equilibrium, okay? So there's no dominant strategy equilibrium. No dominant strategy equilibrium in this case, okay? So let's look at the second example. In this example, I want to add on another thing, okay? In this example, I want to show you what is a Nash equilibrium. The Nash equilibrium describes the optimal state of the game, where both players makes optimal move, but now consider the move of their opponent. What it means is, right, if you want to determine the Nash equilibrium, right, you need to know what other's opponent is choosing. Say if Bala want to determine what is Bala's decision, right, then Bala needs to know what Anil choose. Say Anil choose IPC, then what Bala choose. Say Anil choose Terminator, then what is Bala next move? We will look at the example of Nash equilibrium later, and there can be only one dominant strategy equilibrium, but multiple Nash equilibrium, okay? Meaning, right, after you determine the dominant strategy, example, if this case have dominant strategy, right, after you determine there's one dominant strategy for each of the player, if both players choose to play its dominant strategy, right, then this dominant strategy equilibrium. There can be only one dominant strategy equilibrium, but multiple Nash equilibrium, okay? They can exist multiple Nash equilibrium. However, not all Nash equilibrium are DSE, okay? So it's look like this, okay? DSE is Nash equilibrium, okay? But Nash equilibrium does not necessarily mean DSE, okay? This is the error, okay? So let's look at this example. In this situation, right, there are two planter. The planter known as anil and bala, okay? So they want to decide which pesticide they want to use. There are two pesticides for them to choose. The first type is IPC and the second type is Terminator. So let's look at Terminator first. Terminator helps the planter to save money, okay? It kills every insect. This is a very vigorous pesticide, okay? It kills all the good and the bad insects around. And this Terminator, if say example Bala use Terminator, right? Even Anil use IPC, it will still kill off Anil's good insect, okay? Good insect would go and kill the bad insect, okay? And one more thing, if you use Terminator, right? If the planter use Terminator, it's going to pollute the water supply for both of them, okay? And however, if they choose to use IPC, right? IPC introduce beneficial insects for the farm, okay? The beneficial insects eat the pest insects, okay? So if either one of them use Terminator, then another use IPC, what happens is there is some damage to the insect and also water supply, but it is limited, okay? It's limited. So let's look at this chart. This chart means, right, if Anil use IPC and Bala use IPC, what happens is then the beneficial insect spreads over the both fields, okay? So the beneficial insect would eat the pest, okay? So there's no water contamination. It's a win-win, okay? Win-win. However, right, as I said, IPC is slightly more expensive than a Terminator. This is one thing you need to keep in mind, okay? So for Bala, if Bala use Terminator and Anil choose to use IPC, what happens is Bala's chemical, right, will spread to Anil's field, okay? It will spread to Anil's field and kill the beneficial insect for Anil too, okay? If it kills the beneficial insect for Anil, then it's bad for Anil. And there's a limited water contamination, then Anil is also affected. Then Anil need to install water filter, like water filter for their drinking purpose, bathing and etc., right? For washing. Similar to this situation, if Anil use Terminator and Bala use IPC, then this scenario will be same as this one, okay? So what happens if both of them use Terminator? If both of them use Terminator, right, it will eliminate all pests. However, there is very heavy water contamination and require very expensive filtration system, okay? So if you plot these variables, right, if you consider the value of using IPC, Terminator, the effects, right, the harming effect, and then this is what you get. This is called as a pair of metrics, okay? For example, if both use IPC, right, both have to pay extra money for the pesticide. So say the pair of is 3 and the pair of is 3 for both of them, okay? So if either of one of them use Terminator, right, then say Anil use IPC, Anil will get affected. Anil already use more expensive pesticide. Anil's water get contaminated, and then Anil good pests get killed also. So this is bad for Anil. And then same thing apply to here. If Anil use Terminator, then it's going to affect Bala, okay? So what if both of them use Terminator? Of course, the price they pay for the insecticide is very less. However, they require very high cost for filtration system. This is why the payoff is very less, okay? So without further ado, let's look at this situation. We're starting from Bala, okay? Say if Bala choose to use IPC. If Bala choose to use IPC, what is Anil's dominant strategy? 3 vs 3. If 3 vs 3, right, it is not called as dominant strategy, okay? So let's look at the next one. 4 vs 1, okay? 4 would be beneficial to Anil. So in this case, right, this is the dominant strategy for Anil. So we put a tick, okay? This is just a little mark. So let's look at if Bala use Terminator. If Bala use Terminator, right, 1 vs 4, this is not a dominant strategy, right? Because Anil is worse off. So let's look at this case. 2 vs 2. 2 vs 2 is not a dominant strategy also, okay? So next turn is Anil. Say if Anil use IPC. If Anil choose to use IPC, let's look at Bala. If Bala choose IPC, what happens? 3 vs 3. If 3 vs 3, right, it is not a dominant strategy because both is the same payoff, okay? So if Bala use a Terminator, 4 vs 1. So this is a dominant strategy for Bala, okay? Let's put the tick. So let's look at Anil. If Anil choose Terminator, what happens? If Anil choose Terminator, what happens if Bala use IPC? The payoff is 1 vs 4. 1 vs 4 is not good for Bala, okay? So how about 2 vs 2? 2 vs 2 It's not a good pair-off for Bala too. So this is not a dominant strategy. So what we get in the conclusion? In conclusion, right, the dominant strategy for Bala is to use a terminator, okay? And the dominant strategy for Anil is to use a terminator also. This is their dominant strategy, okay? Then if both of them choose to use terminator, right, then this is called as a dominant strategy equilibrium. Then the answer is, if both of them choose to use the dominant strategy, right? If both of them choose to use dominant strategy, then this is called as dominant strategy equilibrium, okay? So if both of them choose to use their own dominant strategy, right? It's called as dominant strategy equilibrium, okay? So I put this as dominant strategy equilibrium. All dominant strategy equilibrium is known as Nash equilibrium already, okay? Let's go and look at Nash equilibrium. So if you want to look at Nash equilibrium, right, you look at Bala first, okay? Say Bala choose to use IPC. If Bala choose to use IPC, right, what happened to Anil? Is Anil going to use IPC or terminator? Answer is Anil is going to choose terminator. So we put a mark in here. We put a dot in here. So let's look at this. Okay, if Bala choose terminator, right, what would Anil do? What will Anil choose? Anil will choose for, let's see, the pair is 1 vs 4 and 2 vs 2. 1 vs 4 vs 2 vs 2. The answer is Anil will choose 2 vs 2, okay? Anil will choose 2 vs 2. Let's look at Bala. For Bala, right, if Anil choose IPC, right, what will Bala choose? 3 pair of 3 vs 4 pair of 1, okay? 4 pair of 1, okay? So Bala is going to choose 4 pair of 1, okay? Bala is going to choose this. How about if Anil choose terminator, what happened? If Anil choose terminator, right, is Bala going to choose IPC? 1 pair of 4 vs 2 pair of 2. He's going to choose 2, right? 2 pair of 2. This one. So Bala is going to choose this one. Okay? Bala is going to choose this one. So if there's an intersection, right? Then this is called as Nash equilibrium. So the Nash equilibrium will be this one. Okay? Nash equilibrium will be this one. In this example, right? 2-2 is called as a personal dilemma. Okay? In this situation, right? This is known as prisoner dilemma. In our game, Anil and Bala each receive pair of 2, but both of them would be better off using IPC, right? Because IPC gives the pair of 3 and 3 respectively. The predicted outcome is therefore not best feasible outcome, okay? Alright, let's look at the third example, okay? In this third example, right, we got 2 best friends, okay? These 2 best friends, or we can call this them colleague, okay? These 2 colleagues are working together for a project, okay? The first one is called as Bettina. Bettina is very good in C++, okay? And Astrid is very good at Java, okay? So Astrid wants to write in Java because she is better at writing Java. Unfortunately, Bettina prefers C++. For this is a joint project. This project is a joint project, okay? And they will pair based on how many lines of code they have written, okay? This is just an example, okay? In real life, right, you can write very long code doesn't mean you have written very well, okay? But let's just take this as example, say if they are paying based of number of lines, okay? So the true strategy are therefore called as Java and C++. This is the strategy name, okay? Strategy. So we also the same thing. I'm going to walk through with you. So if Astrid use Java, right? If Bettina use Java, what happened? Both work in the same language, okay? If they work in same language because they are using the same joint project, right? Then Astrid benefits more. She is better at Java coding. So the pair of for Astrid is 4. And then for Bettina, the pair of is 3. Okay? What happened if Astrid use Java and then Bettina use C++? Then each is working in the language they are better at, okay? They are working at the language they are better at. But working in different language is got one problem, okay? It's less productive because after they have finished the project, right, they want to combine it, they need to translate it to either Java or they need to translate this one to C++. That's why this is a bit inefficient, okay? So let's look at the pair of. If they each work in the language that they like, right, then the pair of is 2 and 2 respectively, okay? How about if they use the language that they don't like? So if Astrid use C++, if Bettina use Java, right, both use the language they don't like. So neither work fast, okay? Neither work fast. Working in different language is less productive, okay? So they get a 0-0 payoff, okay? The payoff is 0-0. And also if Bettina choose C++ and Astrid choose C++, what happened? Both work in the same language, right? But Bettina benefit more because she is better in C++ coding. So in this situation, you can see Astrid, Bettina Java is 3, right? if Bettina choose to work in Java, it's 3. But for Astrid, right, if Astrid choose to work in C++, it's also 3. The additional benefit gained by Bettina is she is very fluent in C++. Maybe she is more pro, okay? She can complete her work more faster, okay? So she don't need to work overtime. This is just an assumption. So the payoff is 6 compared to this one is 4, okay? So if Bettina prefer to use C++, right, Astrid follow to use C++, this is the payoff, okay? So after we understand this situation, right, let's look at the dominant strategy. So what is the dominant strategy? We are going to look at Bettina first, okay? So if Bettina choose to use Java, right? So Bettina choose to use Java. If Bettina choose to use Java, what happens? If Bettina choose to use Java, Astrid would then choose Java, right? Then this is a dominant strategy for Astrid. Then we got our first dominant strategy. So this is a dominant strategy for Astrid, okay? So we put a tick in here, okay? And how about this one? This is 0, 0, this is nonsense, okay? So there's no point to use this one. So we can skip this part when we are looking at dominant strategy, okay? So let's move on to C++. If Bettina choose to use C++, right? Bettina choose to use C++. What would Astrid choose? 2 vs 2 is not a dominant strategy, okay? No dominant strategy. 3 vs 6, this is not a dominant strategy for Astrid also. No, okay? So let's get to Bettina turn. For Bettina turn, right? If Astrid choose to use Java, what happened? If Astrid choose to use Java, then we are going to look at this row, okay? If Astrid choose to use Java, right? Then would Bettina choose to use this one? No, okay? Would Bettina choose to use this one? This is not dominant strategy, okay? This is not dominant strategy since both is the same value, okay? So what if Astrid use C++? If Astrid use C++, right? It's not dominant strategy also, okay? So how about this one? So if C++, right, in C++, right, Bettina use C++ 6 vs 3, so this is a dominant strategy. Okay? So we put a tick. So in conclusion, right, the dominant strategy for Astrid is to use Java, okay? If Astrid wants to have highest payoff, right, if Astrid wants to have highest payoff, Astrid would choose Java. And if Bettina wants to have highest payoff, Bettina would use C++. Okay, C++, okay. So how do we determine the dominant strategy equilibrium? We determine the dominant strategy equilibrium by combine them, okay? We combine them. So if Astrid use Java and Bettina use C++, right, this is known as our dominant strategy equilibrium, okay? Dominant strategy equilibrium. So the payoff is 2 vs 2. So as you can see, just now in our prisoner dilemma, right, this is the dominant strategy equilibrium, okay? This is the dominant strategy equilibrium. But this is often not the case, okay? Example, in our society, right, if everyone going to drive on the right side, then you are going to follow on the right side. In other country, right, if everyone drive on the left side, then you are going to follow also, right? There's no way you are going to oppose it. So for this situation, right, if in the game theory, if everyone is playing their best to respond to the strategy of everyone else, right, then this strategy are termed as Nash equilibrium, okay? This strategy are termed as Nash equilibrium. So we don't go and look at if you are not going to look at the dominant strategy, right, we are going to look at the Nash equilibrium, okay? Many economic interactions do not have dominant strategy equilibria, okay? But if we can find a Nash equilibrium, it gives us a prediction of what we should observe. We should expect to see all the players doing the best they can, given what others are doing. Each player best response does not depend on what other player does. Unlike in this example, right, for this joint project, right, it's going to be either they are going to use Java or they are going to use C++. So let's look at Nash equilibrium now. If you want to look at Nash equilibrium, right, we need to know what is the other person choosing. Okay, let's start from Bettina. So if Bettina choose Java, right, so if Astrid know Bettina choose Java, right, the pair of 4 vs 0, right, of course Astrid is going to choose Java, right, because Astrid know we got higher payoff, okay? So if Astrid know Bettina choose C++, what happened? So payoff of 2 vs 3, Astrid is going to choose this one, okay? Astrid is going to choose this one. So Astrid is going to choose this one. The pair of 2 vs 3, Astrid is going to choose this. So how about Bettina? So for Bettina, right, if Bettina know Astrid going to choose Java, right, so Bettina of course would going to choose this one, okay? Bettina will choose this one. Because 3 vs 2, 3 have higher payoff. If 3 have higher payoff, right, of course Bettina is going to choose 3. So we put a dot in here, okay? We put a dot. Okay, so let's look at what if asterisk choose C++. If asterisk choose C++, right, what will Bettina choose? Of course, Bettina will choose 6 vs 0, right? 6 vs 0 meaning she's going to choose this one. Okay, so we got true Nash equilibrium here. Okay, if you are going to choose true Nash equilibrium, which one would you choose? The answer is 6, 3. Okay, the answer is 6, 3. They can be multiple Nash equilibrium. Okay, they can be multiple Nash equilibrium. So in this scenario, right, there are two Nash equilibria. You heard I said equilibria. It's a plural, okay? But both choose Java. In one, right, both choose Java. And in other, both choose C++. Can we say which of these two equilibria is more likely to occur? Astrid obviously prefer that they both play Java, while Bettina prefer they both choose C++, okay? With the information we have about how the two might interact, right, we can't yet predict what would happen. In real social interaction, the outcome might be determined by such things. Which of the two has more power? For example, if Astrid is Bettina's boss, then they will probably end up using Java. The second criteria is who started to work on the project first. If Bettina has completed part of the project before her co-worker Astrid is brought onto the team, then they will probably continue to use C++, okay? Let's look at the final example. For our final example, right, we are going to determine the Nash equilibrium for these two guys, okay? Becky and Anthony. They want to decide to go to opera or they decide to go to football stadium, okay? If Becky choose to go to opera, right, what do Anthony choose? Anthony would go and choose opera, okay? Anthony will choose opera. How about if Becky choose to play football? I mean, what happens if Becky choose to watch football? If Becky choose to watch football, for Anthony is better off going to choose football, okay? Football. So this is the higher payoff. How about if Anthony choose opera? If Anthony choose opera, what would Becky choose? Becky would choose football, okay? Becky would choose football. How about if Anthony choose football? So Becky would choose football, okay? So there is one Nash equilibrium in here, okay?